Hi, I'm Josh Isaacson.
I'm Justin Obenchain.
This is Team PC's doing a discussion on Chapter 6.4.2, the materials perspective. So basically the materials perspective describes the forces in each bar of a truss in terms of its elongation, dimensions, and Young's modulus.
Okay, so in our diagram up here, we've drawn out all the internal forces that we don't know. We do know that there's a 1,000 Newton force coming down from joint 1, and that the bars are at 45-degree angles with the horizontal. So basically, we're solving for the buckling load to find out at what point the truss will fail. And for these trusses are made out of aluminum, so we have Young's modulus for aluminum is 70 times 10 to the 9th, so that's where that number comes in from the equation. And we also have to find the moment of inertia, which is given to us in the book from the equation d to the 4th divided by 12. So our d is the width of the truss in this situation, and we come out with 1.6 times 10 to the negative 7th. So to solve for the buckling force, we use the equation force buckling is equal to pi squared times Young's modulus times the moment of inertia, all divided by length squared. So when we put our numbers in up here, we get 1104 newtons. For a previous problem, we know that the internal forces in the truss are 707 newtons, and since that's less than the buckling load we found, we will then know that the truss won't fail when the internal force is put on it.
Okay, so now we're going to solve for the internal forces within the bar based on the Hooke's law relationships. Because each bar is the same length and has the same angle, then each of the forces in them are going to be equal. We can write out these forces as the internal force between joints 1 and 2 is equal to Young's modulus for aluminum, the area between 1 and 2 divided by the length times the change in length. And the internal force between joints 1 and 3 is going to be Young's modulus times the area divided by the length times the change in length between of the bar between joints 1 and 3. Then, in order to solve for the elongation, which is the change in length, because both bars are equal and have an equal force on them, we know that the change in length of the bar between 1 and 2 and 1 and 3 is going to be equal to each other. So we can set this equal to, using our two equations over here, we can set this equal to the internal force between joints 1 and 2 times the length divided by Young's modulus times the area. So plugging in all of our numbers for that, we get an elongation of negative 0.25 millimeters. So this means that instead of stretching or expanding, we have both bars are compressing.
That was Team PCs with another fantastic video.